In this video, we are going to learn the most important rules for simplifying roots. If you're not confident with the basics of roots, feel free to check out my video called Intro to Roots. I put a link in the description box. Let's start with the square root of 900. The multiplication rule for roots says that we can split up a root with a product under it into a product of two roots. So the first step we have to do is to make sure that we have a product under the root. That's simple. Just write the 900 as 9 times 100. Now we can use the multiplication rule for roots and write the square root of 9 multiplied with the square root of 100. The square root of 9 is 3 and the square root of 100 is 10. So we get 3 times 10, which is 30, and we are done with this problem. This method also works for the nth root. In other words, this also works for the third, fourth, fifth root, and so on. In general, we can write this rule as the nth root of AB is the same as the nth root of A multiplied by the nth root of B. But be careful, this rule doesn't work for the addition and subtraction of roots. I want to establish that in this rule and the following rules, the variables a and b have to be real numbers, variables or algebraic expressions, so that the indicated roots are real numbers. And m and n should be positive integers. Let's try the square root of 18. Eighteen is not a perfect square like 1, 4, 9, 16, 25, and so on. The square roots of these numbers are integers. They are 1, 2, 3, 4, 5, and so on. But the square root of 18 is not an integer. The square root of 18 is 4.2426 and so on. This number never ends, but most of the time we want to express this number in a better way, which we can do by using our multiplication rule for roots. So how can we write the 18 as a product of two numbers? That's simple. We write the 18 as 2 times 9. And then we can use our multiplication rule for roots. The square root of 2 multiplied by the square root of 9. This method is also called partially taking the root. In other words, we don't take the square root of 2 because the solution is not an integer. But we take the square root of 9, which is the integer 3. We write this as 3 times the square root of 2. What if we write the 18 as 3 times 6? In this case, we can take either the square root from 3 to get an integer as our solution, or take the square root of 6 to get an integer as the solution. So always try to factor the numbers that way so that at least one of them simplifies as an integer. Let's look at an example where we can use the division rule for roots. What is the square root of 25 over 36? If we didn't know the division rule for roots, we would start by dividing 25 by 36, because the operation of division has priority over taking the square root. Do we really want to do long division here? Fortunately, we can use the division rule for roots here, which makes finding the solution much easier and much nicer. So we can write the square root of 25 over 36 as the square root of 25 divided by the square root of 36. We see that the division rule for roots divides the square root into two separate square roots. In general, we can write this rule as the nth root of a over b is equal to the nth root of a divided by the nth root of b. So the square root of 25 is 5, and the square root of 36 is 6, and we are done with this problem. Let's do one more example with the division rule for roots. How can we simplify the square root of 5 over 16? Feel free to pause the video and try this yourself. Again, we can split up the square root to the 5 and to the 16. And again, we don't take the square root of 5 because the solution is not an integer. But we take the square root of 16, which simplifies to the integer 4. Let's look at the rule for roots, where we change the order of the operations. The third root of 8 squared is the same as the third root of 8 in parentheses squared. In other words, at the left expression, we first square the 8 to the 64. Because 8 times 8 is 64, and then we take the third root of 64, which is 4. Because 4 times 4 is 64. And at the right expression, we first take the third root of 8, which is 2. And then we square the 2, which gives us 4. This rule clearly shows that it doesn't matter if we first raise to the power and then take the root, or if we first take the root and then raise to the power. So in general, we can write the mth root of a raised to the power of n is the same as the mth root of a in parentheses raised to the power of n. Let's do one more example with this rule and look at the third root of 2 raised to the power of 4. The rule says we can change the order of operations and first do the root and then the exponent. So let's move the 4 outside the parentheses and put the root in parentheses. But is this really true? Let's find out by checking if the left side is equal to the right side. Maybe it's helpful to write the root as an exponent. Let's try this. By using the rule that the nth root of a raised to the power of m is the same as a raised to m over n. This rule converts an exponent into a root and a root into an exponent. So we get 2 raised to 4 over 3. Let's look at the right side if we get the same solution. With our rule, the third root of 2 is 2 raised to 1 over 3. Don't forget the parentheses and raise that to the power of 4. Now we need the power of power rule for exponents, which says that we can multiply the exponents. So we get 2 raised to 1 over 3 times 4. 1 over 3 times 4 is 4 over 3. And we get the same on the right side, 2 raised to the power of 4 over 3. Let's look at an example where we can use the next rule, which is about nested roots. The fourth root of the third root of 2 is the same as the 4 times 3 root of 2. In general, the rule is written as the mth root of the nth root of a is the same as the m times n root of a. Like in the previous example, it's helpful to write the roots as exponents, because the nth root of a raised to the power of m is equal to a raised to the power of m over n. The third root of 2 is equal to 2 raised to the power of 1 over 3. Now we do the same thing again. Feel free to pause the video and try that on your own. If you have problems, just use the rule written below. What does the rule say? First, write the base, which is 2 in our example. Second, the 1 over 3 goes on the top of the fraction of the exponent of the 2. And third, the 4 goes on the bottom of the fraction of the exponent of the 2. Now, what is 1 over 3 divided by 4? Dividing fractions is just keeping the first fraction and multiplying by the inverted second fraction. So we get 2 raised to 1 over 3 times 1 over 4, which is 2 raised to 1 over 12. If we want, we can write this also as a root. Feel free to pause the video and try it on your own by using the rule in reverse now. The top number of the fraction, which is 1 in our example, becomes the exponent of the number 2, and the 12 in the bottom of the fraction becomes the index of the root. Two raised to the power of 1 is 2. And we get the 12th root of 2. Let's check if we get the same with our expression on the right side. 4 times 3 equals 12. So we get the 12th root of 2, which is exactly the same as our expression on the left side. Let's do one more example with the nested roots and look at the third root of the square root of 1. According to our rule, we have to multiply the indexes of the roots. Remember, if there is no index like here in our square root, we can imagine that it has the index 2. So we get a square root with an index, which is 3 times 2, which equals 6. And we get the 6th root of 1. The 6th root of 1 is 1, because 1 multiplied by itself 6 times equals 1. Let's look at the left side. The square root of 1 is 1, because 1 times 1 is 1. And the third root of 1 is 1, because 1 times 1 times 1 is 1. So we get 1 as our solution. So we have a 1 in our solution on the left side and a 1 in our solution on the right side, which means we applied the rule for nested roots correctly. Let's look at the next root with the following expression. The square root of 9 is 3. And raising that 3 to the second power gives us 9, with which we started. The square root of 16 is 4. And raising that 4 to the second power gives us the 16 with which we started. The square root of 25 is 5. And raising the 5 to the second power gives us the 25 with which we started. We see that the square root and the raising to the second power do cancel each other out. The interesting thing is that this works not only for the square root and the exponent 2, this also works for taking the third root of a number and then raising it to the third power, or taking the fourth root and then raising it to the fourth power, and so on. In general, we can write this rule as the nth root of a in parentheses raised to n is equal to a. So as an example, when we have the third root of 27, which is 3, because 3 times 3 times 3 is 27, and then raise the 3 to 3, we get the 27 we started with. Because 3 raised to the power of 3 is 27. We use this when solving equations a lot. For example, let's say we have the square root of x equals 3. How can we remove the square root from the x? We just raise both sides of the equation to the power of 2. On the left side, the square root and the exponent 2 cancel each other out, and the x is by itself, which is what we wanted, and on the right side we get 9. So we solved the equation, the square root of x equals 3 to x equals 9. This is a very simple example, but it shows best how the rule works. For the sake of completeness, I have to say that this doesn't work for negative numbers. Let's look at the last rule. The nth root of a raised to the power of n is the absolute value of a when n is even. And the nth root of a raised to the power of n is a when n is odd. Let's do two examples for n is even and for n is odd. We are starting with the even n. When we apply our rule to the square root of negative 3 squared, we get the absolute value of negative 3, which is 3. Let's see if this is really true. Negative 3 squared is 9. And the square root of 9 is 3. So this is true. What about this example? The square root of negative 2 squared. When applying the rule, we get the absolute value of negative 2, which is 2. Let's also check to see if it is really true. Negative 2 squared is 4. And the square root of 4 is 2. So this is also true. Let's look at two examples when n is odd. The third square root of negative 3 cubed is negative 3 according to the rule. Let's check if this is true. Negative 3 times negative 3 is 9, times negative 3 is negative 27. And the cube root of negative 27 is negative 3, because negative 3 times negative 3 is 9, times negative 3 is negative 27. What about this example? The third root of negative 2 cubed. According to the rule, this is negative 2. Let's check it. Negative 2 times negative 2 is 4, times negative 2 is negative 8. And the cube root of negative 8 is negative 2. So this is also true. I want to add two important things at the end of this video. First, I will make a video after this with a lot of more examples and also examples about how these laws also work in reverse. Second, I highly recommend you start memorizing these laws, so it's much easier to follow the upcoming video with the examples. Apart from that, these laws are the absolute basics and required knowledge in math. If you have any questions, feel free to ask me in the comments. This video is what I did for you. If you want to do something for me, hit the bell button, share and subscribe. Thanks for watching and happy learning, everyone.